that presentation. You see that making a price in the from the Instituto Tecnológico de Culiacán in Mexico in 1997, and the using free and automatic control. He was a postdoctoral fellow at the University of Citedi-IPN from 2004 to 2005. Currently, he's a Citedi researcher. His main research interests are in control of electromechanical systems and design for mechatronic systems. So, please.
Thank you very much for the introduction. Possibly most of you are tired and possibly starving, so I want to try to make compact the presentation because we will go to have lunch, okay? And this work has been done in collaboration with Manuel, who was a Master of Science student here in Citedi. And we found an interesting problem in boost power converters. So I have divided the presentation in 6 sections. The first one is the introduction. Second, I'm going to talk about a controller server by Carellani, Spolsky, and Ortega. The third section is about dynamic stability analysis, then some experimental results, and then a conclusion, and finally some open problems and future readiness. So we have that boost converter is a type of DC to DC power converter with an output voltage that is greater than its input voltage. Application of these power converters is in different types for generators, such as wind generators, solar generators, and different subsystems and hybrid automobiles. So we have applications in battery power circuits too. Essentially, this power converter is composed in 5 elements. We have here an input voltage, we have here an inductor, we have here a capacitor, and then a resistance that is the load of the system. An important element of the boost power converter is the switching element. The task of the switching is close the circuit, then the inductor is going to be charged with a current, and when the switch passes this place, the current that is loaded in the inductor is going to be transferred to this circuit. Essentially, this is the way that this system is working. The purpose of this slide is no debate or introduce you about the boost with modulation concept. Here we have a green signal, which is here. This green signal is compared with respect to a triangle wave signal. So from the comparison, we have a triangle, a square signal. This square signal can be used to perform the commutation in the boost power converter. So by using this concept, we have an average model of the boost power converter here, where U is called the direct cycle percentage. This model is second order, it's nonlinear, and has been very studied in the last 10, 20 years. And we have that most of the reported documents in the literature do not consider the input constraint of the direct cycle percentage. We have here three examples. They are concerned about the nonlinear control schemes, but they are not worried about the problem of saturation of the direct cycle percentage. So when we realized this situation, we decided to look for schemes which which consider the input constraint of the data set percentage. We only found three papers on this subject. The first one by Rodriguez and others introduces a very simple feedback control law, and they show that the control law can be produced limited control action in our region of the state space. A more exotic design is found in the Citedi-IPN and Ortega paper, and more recently, Leiva and others introduced model-based saturated controls. Okay, what can you find? What can you find in this talk? You can find new results on control of input constraint boost power converters, and a brief discussion on the open problems that I believe are worthy of investigation. The control problem I'm going to talk about in the next is the following. First, let us assume that the output voltage is the only measured state. This means that the induction current is not measured. Let us consider that the supply voltage is unknown, and then the control problem is to decide a control law that computes the data set percentage, which is limited to this set, so that the output voltage goes to the decided output voltage when the time progresses. Here is a diagram explaining the control problem. We have here feedback of the output voltage, and then we have the controller, and between the controller and the boost converter we have a nonlinear saturation function, which we introduce we complicate the problem for stability. A paper that solved the problem I already explained is a paper by Citedi-IPN, and Ortega. They proposed that the controller observer, and the controller has the characteristic that satisfies the constraint of the saturation of the 30-second percentage. However, we realized that the stability analysis was not completely studied science. No conclusion was provided for the electrical aerodynamics. So we decided to study this problem. Here is the observer proposed by Citedi-IPN, and Ortega. This observer is inspired in the nonlinear dynamics of the boost power converter, and with the solution of this couple of differential equations, we can estimate the input voltage as well as the conducting current. By using these chains of variables, we can find the observation aerodynamics. Citedi-IPN showed that the steady space of the origin of the steady space system is asymptotically stable. They use the H infinity norm and the small gain theorem, and they use this controller which resembles the well-known open loop controller. As I already said that no solution.
Switches the separation moment. Because what I'd like to understand,
yes,
where is the switches here? Because you start showing us some switches, and then where are the switches in your model?
Okay, let me go back a few slides. Okay, what you can find in the textbooks about power converters is that they use an average model. This model is continuous. Yes, this model is continuous. And then,
but the frequency is fixed. So the swing frequency is the swing question now is maybe more of the usage. There are two modes to go for search. One is our PWM.
Yes.
And you are putting fixed frequency in your command.
Yes.
So you are making, so that's a big difference with, for example, when you are using feedback and the frequency of switch. The frequency of our oscillation of the system. So you will restrict yourself from PWM case.
Okay, let me see if I understood your question. Okay, first, we have a control signal that is due here. The way that the controller is implemented is by comparing this continuous signal with respect to this time shaped signal. The frequency of this signal should be big enough to the assumption, for the assumption of a continuous model to be satisfied. So yeah, that's this frequency is can be estimated. You have
when you are using another and you are saying, okay, I will switch with a prescribed frequency.
Yes.
The other way is to keep the system to leave the system work and then out oscillation will arise. That's the point. So which one of two cases you are following? Because it's a crucial question for such a system. You know that the sliding windows will start from such type of movement, but the problem is that people conflating these work and the frequency of these signals will establish themselves because it is what the system is really produced for infinite frequency, which asking for a sliding. Another approach is put PWM. What's the restriction here? PWM is normally less frequency, so less precision, and stuff like that. So, and in that case, you have to work with other information. There are two types. One is fixed frequency, and another one is oscillation. So that is why I'm asking you about, because you are using two statements. So you are starting from a equation.
Yes, that's right. Yes.
What's the nature? What's the nature of the equation? You let them to work with a fixed frequency or with some. That's two different.
Okay. I'm not familiar with the problems that you are talking about. In fact, I am starting the research. Yes, for me, we are starting
so
1 year and a half ago.
You put here PWM,
yes.
You suppose that this is model with PWM. Pay attention that there are two approaches. The system could be non-linear phase.
Yes, that's right. I know that there is a lot of problems with nonlinear effects about the switching. There is a lot of problems with the. In fact, there is other type of non-linearities in inductor. I have the knowledge about that, but my research is constrained. Is focused only on the assumption that this system can be modeled like this. But I know.
You know how he's calling the cycle of community?
No.
General of converters.
General converters.
So general of converters.
General of converters. Okay.
That is why when you started to speak about that, and you haven't mentioned Professor Sierra, Professor. You mentioned Professor Sierra.
Yes,
Yes. We please pay attention because it is, let's say, that is why he is working with such stuff. He also was will see relation.
Yes, I have read some papers on that kind of stuff. But, I mean, by the.
So, and there are two versions.
Okay, I will do that. Thank you. Okay. Okay, I was saying that the observation error of the observer proposed by Karayanis is given in this equation. They use H infinity norm and small gain theorem to show that this system, that the space origin of this system is asymptotically stable. So they combine the observer with this controller, which assembles this open loop controller. So no conclusion was provided on the overall closed loop systems, which includes electrical aerodynamics. What I'm trying to say is that they only were concerned about the observation error and nothing was said about the electrical aerodynamics. So we decided to finish, we decided to complete stability analysis for this scheme. So we started with the formulation of the saturation function, psi minor and psi minor are three positive constants that should satisfy this inequality in order to guarantee that the closed loop system has an admissible equilibrium point. So by defining these errors, which are the difference between the induction current and the desired induction current, the difference between the output voltage and the desired output voltage, we computed the aerodynamics of the electrical part, which is given in two parts. Here we have a linear part, a very nice linear part, which if we neglect these two terms, this linear is exponentially stable. And this part is introduced by the observation error and the saturation function. In particular, we have here a function what we call S bar, and this is the profile function S bar. We can check here that for C1 equal to 0, this function is null. So, in other words, when the observation error is null, this disturbance disappears. So, the overall closed loop system can be written in the following cascaded form. We have here an independent system. We have here the electrical aerodynamics that is affected by the observation error. We were looking for stability tools to analyze the overall closed loop system, and we found that the theorem 1 by Loria and Leon Morales matched the structure of this system. So there is 4 steps to verify theorem 1. So I'm not going to explain that. But if you follow that theorem, you can prove that the electrical errors and the observation error goes to 0 when the time progresses. So we have here some experimental tests in order to check theory. Here is a block diagram of implementation. We have here a boost converter, a PWM circuit, some sensors to achieve feedback, a data acquisition board, and a PC running Simulink and MATLAB in order to implement in real time the experiment. So, in order to test the robustness of the observer, we decided to use time varying input voltage, a the beginning, we have an input of 10 volts, and then after 1 seconds, this voltage falls to 6 volts. We selected side minor equal to 0.1, and side major equal to 0.9. Parameters are for the saturation function. These are the parameters of the boost converter. Dv is equal to 15, and that is the decided voltage. Here are the results. This is the control signal. That is a percentage. We have here the saturation occurs in this small area time. And we have here the comparison between the estimated input voltage and the measured input voltage. So after some time, we have that the estimation approaches the voltage that is at the input of the boost converter. We have here the time evolution of the output voltage, and this line represents the desired voltage. After some time, we have the output voltage approaches the decided one. The same situation is when the input voltage falls and the system is recovered after some time. Here is the comparison between the measured inductor current and the estimated inductor current. So we check experimentally that control is working okay. So, conclusions, we have presented a theoretical and practical study of a control observer proposed by Carayanis, Scott, and Ortega. We provided stability analysis of the overall closed-loop system, which includes the electrical part and the observation part. The theory of state system was used, and experimental results confirmed the robustness of the Carayanis scheme. We believe that some interesting problems are the study on robustness with respect to load variations. Here, it's interesting to add an adaptive part for estimating the resistance of the output. We believe that extensions of these results would be interesting for other types of power converters, for instance, the Buck converter, and also the extension to interconnection of several power converters. We also believe that the inclusion of an electromechanical system below is a good problem. Finally, we have here a brief list of the results that we have published in this problem. For instance, in this one, are the details of the stability proof of the Carayanis, Scott, and Ortega scheme. In this journal, we published the results about a new controller, which is model-based, but this controller needs to know the input voltage and needs to the inductor current to be measured. Here are some experimental implementation reported too. And finally, this would be a combination between this scheme and the Carayanis observer, and this is submitted to the ACC conference. We will see